All right, hello. So in this video, we will be exploring the sampling distribution of sample means and get into the central limit theorem. And so our goal is that by the end, we'll be able to find probabilities with dealing with problems that have sampling distributions of the sample means, so sampling distribution of the X bar, and also be able to answer questions dealing with conceptual factors like the shape of it, its standard deviation, its mean, that sort of thing. All right, so let's start by building some intuition, and we're gonna look at this problem here that shows the population distribution of stolen bases for all 1,341 Major League Baseball players that had at least one appearance in the last recent season. So you can see it's really skewed to the right. It actually goes all the way to 70, it says, but it gets cut off at 20 just because it would just take up too much space, and you wouldn't really be able to see anything. Now the histogram below shows the distribution of 100 simple random samples of size 45. So essentially it took 45 individuals from here at random, calculated their mean, and then plotted it. And it did that 100 times. Now, one of the things we want to notice, that we should notice, is how the shape is changing. This one's clearly skewed to the right, but this one is still skewed. It starts to kind of get a little more centered here, and this far less. This only goes from 1 to 7. This is on actually a different scale than that, or actually it's not the same scale, but you can see starting to get it's more squared together, so it's far less spread out. So let's see what this means in terms of how we do calculations involving sample means. All right, so to gain some insight on how these distributions work, we're gonna play around with this app. It's you can find it if you just go online Facebook. So let's kind of first understand what's going on. So this is the population of the action. This is a true population shape. It's normal. It has a mean of 16, median 16, standard deviation of 5. No skew and kurtosis. You guys, we won't really go into that in AP stats, but that just kind of talks about how different it is from normal, how skewed to the right or left. But again, don't worry about that. Now, what happens here is we're gonna take a sample, and what it does is it takes a sample of size 5, so it grabs 5 individuals from the population, and it calculates the mean. So these are the 5 individuals it grabbed from here, and here's the mean. Let's do it again. Let's see what's going on. And there's another mean from another. So now we have 2 statistics. We did twice. 3, another 5, 5. And let's go ahead, let's do this 10,000 times. So that's basically a sped up version, 10,000 times. And here's what we got. You can see that this pretty much looks normal, just like the parent population. However, it's not as spread out as this one. The mean is 15.95, which is pretty much the same as the population mean at 16. However, the standard deviation is only 2.26, whereas the population has a standard deviation of 5, so it's still less than half. Now let's go ahead. Let's see what happens if we increase the sample size. So we're gonna go ahead. We're gonna clear all that, And this time we're going to go ahead and take a sample size of, let's say 20. And again, let's just, this is an idea what we're doing. So this time we're taking 20 individuals. There you go. And calculate the mean of 20. And it's just one statistic. So again, we're calculating the mean from 20 individuals that we take from the population. Here they go, these little blocks. Here's our second one. They're both the same. Now we're just gonna go ahead. Let's do 10,000. And there we go. And let's do another 10,000. So now we have 20,000 reps, 30,000 reps, 40, 50. Let's go to 100,000, 80. It's a little more than 100,000 reps. We did 100,002. So each of these had a sample size of 20. The mean ended up being identical to the population mean of 16. The standard deviation though actually became smaller. It's actually only 1.12 instead of 5. And if you remember in the previous trial, it was about like 2.26. Again, when we're dealing with, as you guys are going through the course, you're gonna have to answer, more involved problems involving, inference methods. And you're always gonna want to understand the population characteristics. So the shape, the center, the spread. You're always gonna want to know what the population shape is, what the center is, and what the spread is. So we can basically say intuitively that the shape of a sampling distribution will be normal or will be approximately normal if the parent population is approximately normal. The mean will be about the same, again, because it's an unbiased estimator, which we covered earlier. So the mean will actually be equal to the population mean. However, standard deviation will be smaller by a certain factor. We're gonna get into the formula in a bit. So less spread out, shape is the same, but the center are equal. All right, let's go ahead. Let's look at the practice problem now. Okay, so here's a summary of what we learned from that simulation activity. So if the population distribution is normal, then so will be the sampling distribution of the sample mean of X bar. It doesn't matter what size your samples are. What does change though is the standard deviation value. Now, the formula for the standard deviation of the sampling of X bar will be the population standard deviation, sigma, divided by the square root of sample size. So sigma divided by the square root of n. As long as you take no more than 10% of the population. It's also known as the 10% condition. We can go into the math and the rigor of it later on, but for now, that's not too important. You be able to do these problems. So let's look at this example. So at the peanut company, dry roasted shell peanuts are placed in jars by a machine. Distribution of weights in the jars is approximately normal. Cool. Has a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Okay, so part A. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding the average contents weigh less than 16 ounces. So which one would be more likely? Would it be more likely that you could just grab one random jar out of all the jars and it would weigh less than 16 ounces? Or would it be likely that you could grab 10 random jars, add all their weights together, divide by 10, and see if it's less than 16? So this is kind of like, again, you got to use some intuition and just your kind of, I guess, like your common sense of how the real world works. But we would say that it would be more likely to grab one single random jar and it would weigh less than 16 ounces because groups of individuals have less variability when we're measuring, like, the mean or something. It's more likely that you can grab one and its mean will be lower, or its value would be less than 16, then you'd grab 10 and take the average of those 10, and their mean would be 16. But now let's look at, now let's actually, do the calculation and see what it is. So let's find the probability that a randomly selected jar contains less than 16 ounces of peanuts. So we're actually going to see what the chances are to select one. Okay, so when you're doing these problems, make sure you define your variables and all your, all what you're working with, like, what your mean is, what your standard deviation is, what your variables represent. So we're going to have X, that'll be the weight of a single randomly selected jar measured in ounces. And so we're trying to find the probability that X is going to be less than 16. And now we have to address the distribution. So this will be approximately normal because the population is approximately normal. And since we're not taking a sample size, since we're not taking a multiple, we're not taking a group, you're just basically using this. You're just using this as your mean, and this is your standard deviation. So this is actually just going back to chapter 2. So don't overthink this problem. This is just like a problem. You could have done this. You could have done part B from what you learned from chapter 2 when you just were introduced to normal distributions. All you're trying to find is the probability that X is 16 in a normal distribution with a mean of 16.1 and a standard deviation of 15. Because remember, we're only looking at one individual. So for this, we can use our calculator. Go to distribution, normal CDF. Since we're trying to find less than, we're going to have a lower bound. We'll just say negative 10,000. The upper bound would be 16. Our mean would be 16.1. And our standard deviation will be 0.15. So there's a syntax. You have this type of calculator. Some calculators are much easier to work with because it lists the mean, standard deviation, lower bound, upper bound. But for these ones, you have to memorize it. All right, so let's see what we get. So we get about 0.25, about 25%. Now, when you do these problems on your actual exam, make sure you write something in terms of how you got your values. The readers want to see some, the readers want to see some justification. They don't just want an answer. So this would be a good way. I usually list it. We use the command normal CDF, lower negative 10,000, upper 16, the mean is 16.1, and standard deviation of 0.5. Gives us a probability of about 0.25. And always make sure to finish your problem with an answer in the context. So our final, answer written something like, there's going to be about 25% chance that a randomly select single jar will weigh 16 ounces. All right, so now we're going to look at part C. So part C, we're trying to find the probability that you would select 10 randomly, you would randomly select 10 jars, and their average weight would be less than 16 ounces. The find probability that 10 randomly selected jars contains less than 16 ounces of peanuts on average. Okay, so now this is where we're going to apply some of the principles that we learned in this chapter. So first, again, let's define our variable. We're taking a sample mean. We're not taking a single individual value. So we're going to say, we're going to have X bar represent the combined weight of 10 randomly selected jars measured in ounces. And so we want to find the probability that X bar is less than 16. Now we're going to have to then address the distribution. So we have to address what the shape would be, center, and spread or standard deviation. So since the population distribution was told to be approximately normal, we could say that the sampling distribution could be approximately normal. And then we then for the standard deviation, we have to then check the what's called a 10% condition. Make sure that we don't take more than 10% of the population. And again, it's usually going to be always the case that 10% condition will be satisfied. They're not really ever going to be problems that that work. Otherwise, you wouldn't be able to do it. But you have to make sure you address it to show that you know what you're talking about. So essentially, we're basically saying that there's at least 100 jars in the population, and that's reasonable to assume. So since we can say that, then we can use the formula for the standard deviation of the sampling distribution of X bar. Remember, that's sigma over the square root of n. So 0.15 divided by the square root of 10, and that gives us about 0.04743. And our mean, again, of the sampling distribution of X bar is equal to the population mean of 16.1. So now we could just, run a calculation that we've been, already learned how to do, since chapter 2, with these as our standard deviation and mean. So we could use our calculator, find the probability that X bar is less than 16. So our lower bound would be like negative 10,000, upper would be 16. Our mean would still be 16.1. However, our standard deviation would change. It would be 0.04743. So let's go ahead, let's do that. So go to normal CDS. So pretty similar to the previous part. Upper bound 16. Whoops, mean of 16.1. And our standard deviation of 0.04743. And whoa, I messed up. That's not good. What did I do? Normal CDS over. Oh, I took 2 commas. I actually did that on purpose. I want you guys to learn how to not avoid these mistakes. So let's do it again. Comma 16.1. Our mean, our standard deviation, 0.04743. And we get about 0.017, so a little less than 2%. So again, when you use technology, that's fine on your AP exam, but make sure you write something about how you got your answer. And I usually recommend this sort of format. And so, our answer, basically agrees with our intuition that it is going to be much more, common to select one jar that weighs less than 16 ounces than a sample of 10, an average rate of 16 ounces. And so make sure we always write down answer in context to make sure that you address or to make sure you can show to the grader that you actually understand what you're doing. Remember, like when the readers look at your work, they have to go by what you write. You're not going to be there. You're not going to be able to talk to them. So if you just put this answer, they need to see if you actually understand what this answer means. All right, so now we're going to see what happens when we have population distributions that aren't normal, because in real life most population distributions aren't going to be normal. So we're going to go back to this applet to build some intuition of what happens. So we're going to change the shape to, let's say, skewed. Let's do this. And well, my mouse is lagging. We're going to go ahead and take a small sample, size 2. Down here, we're also going to take a sample of size 5. So it just does it twice, so we save time. So this one's going to show distribution when we're taking samples of size 2, and this is going to show distribution when we're taking samples of size 5 of the. So let's go ahead. Let's just let's do an animated just first just to see what's going on. So there we go. We're taking. It took 2 for this one, calculate the mean, and for this one, 5. Took those 5 and calculated the mean. So again, it's going to take 1, 2, does this one, then 1, 2, 3, 4, then does that one. So let's go ahead. Let's speed this up. Let's do 10,000. What we got? Stare at that for a second. Let's do another 10,000 or 20,000. Another 10,000, 30, 40, 50, 60, 70, 80, 90, 100,000. And so what you can notice is that the shape of sampling distributions for both of these, aren't, as skewed as this one. They're actually starting to be somewhat normal. We can actually fit a normal curve to it, and you can start to see that it starts to approach it. And this one is, a lot closer. So let's go ahead, let's clear this and see what happens. Let's see what happens if we do, let's do 10, and let's do 20 for this one. So we're going to take samples of size 10, calculate the means on here, and samples of size 20 and calculate the mean of here. So we just do 5 of each. That's what we get. And now let's go ahead, let's do another 10,000. Another 10,000, 20, 30,000, 40, 50, 60, 70, 80, 100,000. And you can see like what the, this is actually pretty cool. I think it's, I'm obviously a math geek, but even though this distribution is skewed to the right, these sampling distributions are approaching normal. So let's go ahead, let's see what happens if we just make some crazy, like, out of this world distribution. Let's like do something like this. Let's do that. Let's do this. We're gonna do that. Who knows what this represents? But let's go ahead. Let's take samples size 10 again and samples of size 20. And we're gonna go ahead and just calculate 10,000. Another 10,000. I don't know why I could probably just press 100,000. I kind of like clicking this, but as you can see that even though the population, has this crazy shape, I don't even know what you call it. I don't know if there's actually a word to describe it, but even though it's some weird, strange shape, when we calculate the sample means, from sample size 10 and sample size 20, their shape pretty much starts to become normal. And these samples are only of size 10, and this one's only of size 20. And so this is, one of the most, I would say, interesting principles in all statistics, and allows us to do all sorts of probability calculations in the real world. And this is essentially what is known as the Central Limit Theorem. So let's go ahead, let's look at the formal definition of the Central Limit Theorem. All right, so here it is. So what the Central Limit Theorem says is that if you draw a simple random sample of size n from any population, so be any weird looking population, has a mean of mu and a finite standard deviation sigma, then when the sample size n is large enough, the sampling distribution of the sampling mean of the sample mean will start to become approximately normal. Now, what qualifies as large enough? Usually most courses will agree with 30. So as long as n is 30, we can apply the Central Limit Theorem. On the AP exam, I think they usually are okay with 25. I know some textbooks go to 25, but 30 always guaranteed to be okay. And again, when you're doing this in your homework problems and on the for response problems, you're always going to be able to have enough, and a sample size is large enough to satisfy this. So we're going to stick with n is 30 for the purpose of the course. And again, here's just some more examples of this Central Limit Theorem at play here. And we want this, I don't know, like a ramp, like a skateboard ramp, half pipe shape. It starts to become normal. Pretty cool, gnarly. And here it is again, formally, what we can say. And again, we like is the boundary level of 30. Want our sample size to be at least 30. Okay, let's go ahead now. Let's do a practice problem so we can apply this in real, in a way that can actually help you. All right, so we say that let's suppose that the number of texts sent during a typical day by students at a large high school follows a right skew distribution with a mean of 45 and a standard deviation of 35. So how likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts in a day? Okay, so let's go ahead and let's start this, and let's break this up into steps. I usually recommend doing these problems in a systematic way, just so that when you're learning them, you can get all your thoughts organized. So the first step is always, define your variable, know what the distribution is, like, what's going to be the center, or what's going to be the mean, what's going to be the spread or standard deviation, what's going to be the shape, and again, we'll justify it, and know what you're trying to find, know exactly what you're trying to find. Again, these problems always be given to you, explicitly. It's not like an algebra where it says solve for x, solve for x, all following equations for the value of x. Sometimes it's easy to figure out, sometimes it's a little more tricky. But what we're trying to figure out in this problem is that the average number of texts sent by these 50 students is 50, because we're talking about 50 sending a total of 2,500. So we're trying to see what is the probability that the average is more than 50 each. Because if we take 2,500 divided by 50, we're going to get 50. So we're going to let X bar represent the average number of texts sent by 50 randomly selected students. So we're going to be looking at the sampling distribution of X bar, where n is 50. Now, we can, say that the mean of the sampling distribution of X bar is equal to 45, because it's an unbiased estimator. So that's always nice. We don't have to really do any extra work. And there it is again. We want to find the probability that X bar is more than 50. We're taking 2,500 divided by 50. And make sure you also practice using the correct notation. It's kind of weird at first, but it makes sense, technically, I guess. So we're, the mean of the sampling distribution of X bar is what we have here, and that's equal to the population mean, which is 45. But what we're actually working with is this. This is what the correct way to write it is. Now, again, to calculate the standard deviation, we have to satisfy the 10% condition. And to basically use a normal distribution, we also have to, check that our sample size is at least 30. So however way you want to word that in your problem, I guess depends on, on your style, maybe your teacher in your class. But make sure you always, again, address what you're trying to find, address the mean, or, the center, the spread or standard deviation, and the shape, in this case, approximately normal. So we're going to check the 10% condition, And again, you could just word it in in a common sense way, because we're told that this is a large high school. So we can say that 50 is less than 10% of all the students at the high school, because it would make sense for a large high school to have at least 500 students. So the population N is at least 500. Now, because of that, we can then use our standard deviation formula for the sampling distribution of X bar, which is equal to sigma, or the sampling distribution of the population, 35, over the square root of N, over the square root of 50. We'll get about 4.95. So we got the center, we got the spread, and now we just need the shape. And since our sample size is at least 50, or sorry, since the sample size is at least 30, we can say that it will be approximately normal. And I like to always put check marks by the key points here. So has the distribution is normal with a mean of 45, standard deviation of 4.95. Since our sample size is 50, which is at least 30. And let me just put a box around that. It's kind of the first time we're using that. Now our step 2 is running our actual calculation. So may not spoil it yet. So we're basically just going to run our normal CDF function, trying to find the probability that X bar is more than or equals to 50. So our lower bound this time is going to be 50. Our upper will be, we can say 10,000. So comma 10,000. Mean of 45. And standard deviation of 4.95. And we'll get about 0.15. So again, just make sure you write something that explains how you got your answer. And then final step, just explain your answer in context. So then we could say there's about 15.6% chance that a random sample of 50 students will have over 2,500 texts in the last day. Or you could also say maybe that they would have on average sent 50 texts each over the last day. Either way is fine. All right, so that's it for that. And by now you should have a good grasp of all the concepts dealing with distributions. So I'll see you next time.